All right, hey AP Chemistry. So I got a request to try and walk us through example 19.8. So you read about an equation, or will be given an equation known as the Nernst Equation. It's Ecell is equal to Ecell standard minus 0.0592 volts over N log of Q. Now, a couple of things with this question to keep in mind with this equation. Let me talk about this equation. Ecell standard you will get from given values. It's kind of like a products minus reactants kind of business, except it's going to be Ecell of the reduction minus Ecell of the oxidation, which ends up being Ecell at the cathode minus Ecell at the anode. 0.0592 volts is a constant. N is the number of moles of electrons. So when you balance each half reaction, which we'll talk about in a moment, when you balance each half reaction, however many electrons are going to be gained and lost must be the same, conservation of matter. So that's going to be N. And then log of Q, Q is the reaction quotient. So it's going to be the amount of our product's concentration over the amount of our reactant's concentration, each of them raised to exponents from a balanced chemical equation. So let's look at what's given to us. It says determine the cell potential for an electrochemical cell based on the following two half reactions. So they told you the oxidation reaction, and they told you that the concentration of copper 2 plus was 0.01 molar, and so it's copper 2 plus was 2 electrons. Now they didn't give you the concentration of copper solid because that's constant and we don't use it. Same thing for the reduction half reaction. They give you permanganate ion, they told you it's 2 molar, you add 4H plus, they told you that's 1 molar, and 3 electrons, and you get MnO2, which is magnesium dioxide, solid, and H2O, water. And those don't have any charges, and they don't have concentrations. So now I have to try and figure out how to start putting in things into the chemical equation. Well, first of all, I could figure out E of the cell, standard, because it's my E reduction minus my E oxidation. Where do I get those values from? Well, if I go flip over back into the chapter, nope, that's too far away. Where do I get those values from? If I look into the chapter on table 19.1, these are all the reduction half reactions, okay? Now, it doesn't matter that one of them is oxidized, one of them is reduced. I use these reduction values to figure out the reduction potential. That's why you do E reduction minus E oxidation. You do E cathode minus E anode. So whatever's being reduced, I find it on here, and that I write first, and I subtract it by the other species that's being oxidized, and I will get the E cell from there. So for example, I have copper and permanganate, and from the table, I get that the E half reaction is 0.34 for the copper, and the E, this is not balanced, right? And E of the permanganate is 1.68. If I want to do E reduction minus E oxidation, or E at the cathode minus E at the anode, I'm going to do 1.68, because this is the reduction half reaction. I'm going to do 1.68 minus 0.34, and I get 1.34. Okay, and that's going to be my Ecell standard that I'm plugging into the equation. Now there's two things left for me to solve for, N and log of Q. Now this is how you get N. It says write the oxidation and reduction half reactions multiplying by the appropriate coefficients to cancel the electrons. Okay, so what does this mean? It means I have to balance the half reactions. So up here I have copper 2 plus and 2 electrons, permanganate, and 3 electrons. Okay. Now, what did they do here? Okay, how did I go from here to here? Well, I lose 2 electrons in the oxidation, and I gain 3 in the reduction. But conservation of matter says I need to gain and lose the same number of electrons. So we have to come up with a common multiple between 2 and 3. The common multiple between 2 and 3 is 6. So if I want 6 electrons, I'm going to multiply this whole top reaction by 3 and this whole bottom reaction by 2. That is why they did that, to have the same number of electrons. It doesn't do anything to your E of cell. E of cell is standard. But now I have my balanced chemical reaction, and this is how I could get my Q. I put my Q of my products over my Q of the reactants. Now, there's only one thing in my product that I could put in the Q, and that is the copper 2+. And remember, copper 2+ had a concentration of 0.01 molar, and that's what I'm going to be putting into the balanced chemical equation. And then I cube it because of the coefficient. On the left side of the reactant side, I can't put in copper solid because solid don't go into the reaction, but permanganate aqueous and the H+ aqueous both go in the reaction quotient, and they already gave you those concentrations of 2 molar and 1 molar. So I plug those in, and of course I put the exponents. The exponents come from the coefficients of the balanced chemical equation. And then all I'm doing now is plugging and chugging. Also, N, why is it 6? Because that common multiple of 2 and 3 was 6 electrons. So N is my number of moles of electrons that both of them are gained and lost. I cannot have this one losing 2 and this gaining 3. That is not even. It is not going to be a conserved matter. I need a conservation of matter, conservation of energy and charge. I need to have the same number of electrons, so I find that common multiple. And then all I'm doing is plugging and chugging, right? I have E of the cell of 1.34. I have 0.0592 volts over 6. 6 is the moles of electrons, times the log of the concentration of Cu2+ cubed. It's cubed because it's a 3 in front, over 2 squared, because it's 2 molar of the permanganate ion, and there's 2 of them squared, over 1 molar of the H+ raised to the 8th power. If I do all that math, I get E of the cell is 1.41. So this is me walking you through example 19.8. There are a couple of things that they might have done a little bit too quick that you might have did not pick up on, but you will have to know how to do this type of question in the future and for your entrance task on Monday. So on Monday, I will ask a question and give you information like this. You will have to balance the half reactions. You'll have to calculate E standard if I give you the reduction potentials, and then you'll have to get your Q value and plug it and chug it into the equation. All right, hopefully this video was helpful in walking you through example 19.8. If you have any other questions or concerns, make sure you comment on the video or message me in the remind.